Section 3.3, Conservation of Momentum. So only when you have an impulse external to a system can you change the momentum of an object. Just like if you have a force external to a system. Force and momentum are inherently linked to one another. Consider when we talk about firing a cannon. Right? When you fire the cannon shoots a cannonball. The cannonball and the cannon experience the same force. Before the cannon's fired, both of those two objects are still at rest. Nothing is moving. Then the explosion goes off, the cannonball goes one way, the cannon goes the other way. This means that before that explosion, before that collision between the gunpowder and the cannon and the cannonball, before that happened, the total momentum of that system, the cannon and the cannonball, was zero. Nothing was moving. With no movement means no velocity. No velocity means no momentum. Now once the cannon fires, the cannonball goes one way, the cannon goes the other way. The cannonball goes really, really far in one direction, and the cannon goes just a little bit in the other direction. Now this is because of the disproportionate masses of the two. The cannonball is much lighter, and so it travels much further, and the cannon is heavier and doesn't travel nearly as far. But if we look at the situation, the total change in the momentum of each one is equal and opposite. So the change in momentum of the cannonball, you see a much higher velocity for a lower mass, whereas the change for the cannon, you see a much lower velocity for a higher mass. And so the two things are equal but in opposite directions. And we know that just like with forces, with momentum, when we have vectors that are equal but in opposite directions, they add to zero. And so that even after the collision, even after the explosion when the cannon goes off, the total momentum of the entire system is zero. And this is true for all systems. And so when we have something in physics, a quantity that we say doesn't change, we say that that quantity is conserved. We'll talk about another one later in this chapter. In this case, what we have is what's known as the law of momentum conservation, which just means that if you do not have external forces or external things occurring to a system, the momentum of that system remains unchanged. The momentum before something happens will be the momentum after something happens. And we can see that with a lot of examples, and you'll see some of those in the videos that I've posted with this section. One way that momentum helps us to understand things that occur in real life is it allows us to understand collisions. Right? Two things before a collision and two things after a collision. Those two things before and after are just a system. If there are no external forces to those two things, then when they interact, their momentum before they interact will be the same as the momentum after they interact, regardless of how they interact, regardless of the collision. Collisions are one thing that we use to illustrate momentum conservation because it's something that you see a lot. There are two different types of collisions. The first is what's known as an elastic collision. Elastic collisions are when you have objects that collide, but there's no deformation or generation of heat, nothing sticks together. Basically, they hit each other and they bounce off. One very good example of this is the game of pool or billiards, where you have balls that hit each other and bounce off. There's no deformation of the balls themselves. They don't break or crack, and they just bounce off. And in fact, pool is actually a really great example of elastic collisions. And if you understand elastic collisions well, you can play pool pretty well. The second type of collision is the one that we're used to thinking of when we think of the word collision, which is what's known as an inelastic collision. And this is where if you have objects that collide, but they stick together or they deform, they break, they fall apart, and they generate heat. These types of collisions are the ones we see most common in everyday life. These types of collisions still conserve momentum, but there's another quantity that's not conserved, that's lost when you generate heat. And that's what we'll talk about in the next few sections.